sigmoid of z is as defined here. So to learn parameters for your model, you're given a training set of m training examples, and it seems natural that you want to find parameters w and b so that at least on the training set, the outputs you have, the predictions you have, x plus b are defined. You need to define a cost function. Let's take a look at a cost function you can use to train logistic regression. To recap, this is what we had defined from the previous slide. So your output y hat is sigmoid of w transpose x plus b, where sigmoid of z is as defined here. So to learn parameters for your model, you're given a training set of m training examples, and it seems natural that you want to find parameters w and b so that at least on the training set, the outputs you have, the predictions you have on the training set, which I'm going to write as y hat I, that will be close to the ground truth labels yi that you got in the training set. So to fill in a little bit more detail for the equation on top, we had said that y hat is as defined at the top for a training example x, and of course for each training example, we're using these superscripts with round brackets with parentheses to index into different training examples. Your prediction on training example I, which is y hat I, is going to be obtained by taking the sigmoid function and applying it to w transpose xi, the input for the training example, plus b. And you can also define zi as follows, where zi is equal to w transpose xi plus b. So throughout this course, we're going to use this notational convention that the superscript parentheses I refers to data, be it x or y or z or something else, associated with the ith training example, associated with the ith example. Okay, that's what the superscript I in parentheses means. Now let's see what loss function or an error function we can use to measure how well our algorithm is doing. One thing you could do is define the loss when your algorithm outputs y hat and the true label as y to be maybe the squared error or 1/2 a squared error. It turns out that you could do this, but in logistic regression, people don't usually do this because when you come to learn the parameters, you find that the optimization problem, which we'll talk about later, becomes non-convex. So you end up with an optimization problem with multiple local optima. So gradient descent may not find the global optimum. If you didn't understand the last couple of comments, don't worry about it. We'll get to it in a later video. But the intuition to take away is that this function L, called the loss function, is a function we'll need to define to measure how good our output y hat is when the true label is y. And squared error seems like it might be a reasonable choice, except that it makes gradient descent not work well. So in logistic regression, we will actually define a different loss function that plays a similar role as squared error, but will give us an optimization problem that is convex, and so we'll see in a later video becomes much easier to optimize. So what we use in logistic regression is that makes gradient descent not work well. So in logistic regression, we will actually define a different loss function that plays a similar role as squared error, but will give us an optimization problem that is convex, and so we'll see in a later video becomes much easier to optimize. So what we use in logistic regression is actually the following loss function, which I'm just going to write out here, is negative y log y hat plus 1 minus y log 1 minus y hat. Here's some intuition for why this loss function makes sense. Keep in mind that if we're using squared error, then you want this squared error to be as small as possible. And with this logistic regression loss function, we'll also want this to be as small as possible. To understand why this makes sense, keep in mind that if we log 1 minus y hat, here's some intuition for why this loss function makes sense. Keep in mind that if we're using squared error, then you want this squared error to be as small as possible. And with this logistic regression loss function, we'll also want this to be as small as possible. To understand why this makes sense, let's look at the two cases. In the first case, let's say y is equal to 1. Then the loss function y hat comma y is just this first term, right? And there's a negative sign, so it's negative log y hat if y is equal to 1, because if y equals 1, then the second term 1 minus y is equal to 0. So this says if y equals 1, you want negative log y hat to be as big as possible. So that means you want log y hat to be large, to be as big as possible, and that means you want y hat to be large. But because y hat is this sigmoid function, it can never be bigger than 1. So this is saying that if y is equal to 1, you want y hat to be as big as possible, but it can't ever be bigger than 1, so it's saying you want y hat to be close to 1 as well. The other case is if y equals 0. If y equals 0, then this first term in the loss function is equal to 0, because y, 0. And then the second term defines the loss function, so the loss becomes negative log 1 minus y hat. And so if in your learning procedure you try to make the loss function small, what this means is that you want log 1 minus y hat to be large, and because there's a negative sign there. And then through a similar piece of reasoning, you can conclude that this loss function is trying to make y hat as small as possible. And again, because y hat has to be between 0 and 1, this is saying that if y is equal to 0, then your loss function will push the parameters to make y hat as close to 0 as possible. Now, there are a lot of functions with roughly this effect, that if y is equal to 1, it'll try to make y hat large, and if y is equal to 0, it'll try to make y hat small. We just gave here in green a somewhat informal justification for For this particular loss function, we'll provide an optional video later to give a more formal justification for why in logistic regression we like to use the loss function with this particular form. Finally, the loss function was defined with respect to a single training example. It measures how well you're doing on a single training example. I'm now going to define something called the cost function to a single training example. It measures how well you're doing on a single training example. I'm now going to define something called the cost function, which measures how well you're doing on the entire training set. So the cost function, J, which is applied to your parameters W and B, is going to be the average, really, 1 over m of the sum of the loss function applied to each of the training examples in turn. Where here y hat is of course the prediction output by your logistic regression algorithm using a particular set of parameters W and B. And so just to expand this out, this is equal to negative 1 over m sum from I equals 1 through m of the definition of the loss function above. So this is yi log y hat I plus 1 minus yi log 1 minus y hat I. I guess I can put square brackets here. So the minus sign is outside everything else. So the terminology I'm going to use is that the loss function is applied to just a single training example, like so, and the cost function is the cost of your parameters. So in training your logistic regression model, we're going to try to find parameters W and B that minimize the overall cost function J written at the bottom. So you've just seen the setup for the logistic regression algorithm, the loss function for a training example, and the overall cost function for the parameters of your algorithm. It turns out that logistic regression can be viewed as a very, very small neural network. In the next video, we'll go over that so you can start gaining intuition about what neural networks do. So with that, let's go on to the next video about how to view logistic regression as a very small neural network. You've seen the logistic regression model. You've seen seen the loss function that measures how well you're doing on a single training example. You've also seen the cost function that measures how well your parameters W and B are doing on your entire training set. Now, let's talk about how you can use the gradient descent algorithm to train or to learn the parameters W on your training set. To recap, here is the familiar logistic regression algorithm. And we have on the second line the cost function J, which is a function of your parameters W and B, and that's defined as the average, so it's 1 over m times the sum of this loss function. And so the loss function measures how well your algorithm's outputs, y hat I, on each of the training examples, stacks up or compares to the ground truth label yi on each of the training examples, and the full formula is expanded out on the right. So the cost function measures how well your parameters W and B are doing on the training set. So in order to learn a set of parameters W and B, it seems natural that we want to find W and B that make the cost function J of W comma B as small as possible. So here's an illustration of gradient descent. In this diagram, the horizontal axes represent your space of parameters W and B. In practice, W can be much higher dimensional, but for the purposes of plotting, let's illustrate W as a single real number and B as a single real number. The cost function J of WB is then some surface above these horizontal axes W and B. So the height of this surface represents the value of J comma B at a certain point. And what we want to do is really to find the value of W and B that corresponds to the minimum of the cost function J. It turns out that this particular cost function J is a convex function, so it's just a single big bow, so this is a convex function, and this is as opposed to functions that look like this, which are not, that corresponds to the minimum of the cost function J. It turns out that this particular cost function J is a convex function, so it's just a single big bow, so this is a convex function, and this is as opposed to functions that look like this, which are non-convex and has lots of different local optima. So the fact that our cost function J of WB as defined here is convex is one of the huge reasons why we use this particular cost function J for logistic regression. So to find a good value for the parameters, what we'll do is initialize W and B to some initial value, maybe denoted by that little red dot. And for logistic regression, almost any initialization method works. Usually you initialize the values to 0. Random initialization also works, but people don't usually do that for logistic regression. But because this function is convex, no matter where you initialize, you should get to the same point, or roughly the same point. And what gradient descent does is it starts at that initial point and then takes a step in the steepest downhill direction. So after one step of gradient descent, you might end up there, because it's trying to take a step downhill in the direction of steepest descent, or as quickly downhill as possible. So that's one iteration of gradient descent. And after 2 iterations of gradient descent, you might step there, 3 iterations, and so on. I guess this is now hidden by the back of the plot until eventually, hopefully you converge to this global optimum, or get to something close to the global optimum. So this picture illustrates the gradient descent algorithm. Let's write out a bit more of the details. For the purpose of illustration, let's say that there's some function J of W that you want to minimize, and maybe that function looks like this. To make this easier to draw, I'm going to ignore B for now, just to make this a one-dimensional plot instead of a higher dimensional plot. So gradient descent does this. We're going to repeatedly carry out the following update. I'm going to take the value of W and update it. I'm going to use colon equals to represent updating W. So set W to W minus alpha times, and this is a derivative, d of JW dW. And we'll repeatedly do that until the algorithm converges. So a couple points in the notation. Alpha here is the learning rate and controls how big a step we take on each iteration of gradient descent. We'll talk later about some ways for choosing the learning rate alpha. And second, this quantity here, this is a derivative. This is basically the update or the change you want to make to the parameters W. When we start to write code to implement gradient descent, we're going to use the convention that the variable name in our code dW will be used to represent this derivative term. So when you write code, you write something like W equals, or colon equals, W minus alpha times dW. So we use dW to be the variable name to represent this derivative term. Now let's just make sure that this gradient descent update makes sense. Let's say that W was over here, so you're at this point on the cost function J of W. Remember that the definition of a derivative is the slope of a function at the point. So the slope of a function is really, the height divided by the width, right, of a little triangle here, this tangent to J of W at that point. And so here, the derivative is positive. W gets updated as W minus a learning rate times the derivative. The derivative is positive, and so you end up subtracting from W. So you end up taking a step to the left. And so gradient descent would make your algorithm slowly decrease the parameter if you had started off with this large value of W. As another example, if W was over here, then at this point, the slope here, or dj dw, will be negative. And so the gradient descent update would subtract alpha times a negative number, and so end up slowly increasing w. So you're making w bigger and bigger with successive iterations of gradient descent, so that hopefully whether you initialize on the left or on the right, gradient descent will move you toward this global minimum here. If you're not familiar with derivatives or with calculus and what this term dj of w dw means, don't worry too much about it. We'll talk some more about derivatives in the next video. If you have a deep knowledge of calculus, you might be able to have a deeper intuitions about how neural networks work. But even if you're not that familiar with calculus, in the next few videos we'll give you enough intuitions about derivatives and about calculus that you'll be able to effectively use neural networks. But the overall intuition for now is that this term represents the slope of the function. And we want to know the slope of the function at the current setting of the parameters so that we can take these steps of steepest descent, so that we know what direction to step in order to go downhill on the cost function j. So we wrote our gradient descent for j of w if only w was your parameter. In logistic regression, your cost function is a function of both w and b. So in that case, the inner loop of gradient descent, that is this thing here, the thing you have to repeat, becomes as follows. You end up updating w as w minus the learning rate times the derivative of j of wb with respect to w, and you update b as b minus the learning rate times the derivative of the cost function with respect to b. So these two equations at the bottom are the actual update you implement. As an aside, I just want to mention one notational convention in calculus that is a bit confusing to some people. I don't think it's super important that you understand calculus, but in case you see this, I want to make sure that you don't think too much of this, which is that in calculus, this term here, we actually write as follows with that funny squiggle symbol. So this symbol, this is actually just a lowercase d in a fancy font, in a stylized font. But when you see this expression, all this means is this is the derivative of j of w comma b, or really the slope of the function j of w comma b, how much that function slopes in the w direction. And the rule of the notation in calculus, which I think isn't totally logical, but the rule in the notation for calculus, which I think just makes things much more complicated than they need to be, is that if j is a function of two or more variables, then instead of using lowercase d, you use this funny symbol. This is called a partial derivative symbol. But don't worry about this. And if j is a function of only one variable, then you use lowercase d. So the only difference between whether you use this funny partial derivative symbol or lowercase d as we did on top is whether j is a function of two or more variables, in which case you use this symbol, the partial derivative symbol, or if j is only a function of one variable, then you use lowercase d. This is one of those funny rules of notation in calculus that I think just make things more complicated than they need to be. But if you see this partial derivative symbol, all it means is you're measuring the slope of the function with respect to one of the variables. And similarly, to adhere to the formally correct mathematical notation calculus, because here j has two inputs, not just one, this thing at the bottom should be written with this partial derivative symbol. But it really means the same thing as, almost the same thing as lowercase d. Finally, when you implement this in code, we're going to use the convention that this quantity, really the amount by which you update w, will denote as the variable dw in your code. And this quantity, right, the amount by which it means is you're measuring the slope of the function with respect to one of the variables. And similarly, to adhere to the, formally correct mathematical notation in calculus, because here j has two inputs, not just one, this thing at the bottom should be written with this partial derivative symbol. But it really means the same thing as, almost the same thing as lowercase d. Finally, when you implement this in code, we're going to use the convention that this quantity, really the amount by which you update w, will denote as the variable dw in your code. And this quantity, right, the amount by which you want to update b, will denote via the variable db in your code. Alright, so that's how you can implement gradient descent. Now, if you haven't seen calculus for a few years, I know that might seem like a lot more derivatives in calculus than you might be comfortable with so far. But if you're feeling that way, Don't worry about it. In the next video, we'll give you better intuition about derivatives, and even without a deep mathematical understanding of calculus, with just an intuitive understanding of calculus, you will be able to make neural networks work effectively. So with that, let's go on to the next video where we'll talk a little bit more about derivatives. you.